we can start with the workshop.
Perfect.
Okay. So first of all, we will do a little presentation because just a little introduction. Because today we will try to tell a story told by our colleagues, which we are presenting today, and based on the experience of the different projects that maybe in a first sight they do not have common characteristics, but in a whole, just in a whole, they work on the different mechanisms regarding to the climate change and from different point of view, especially from technical point of view, of integration of different services and different activities and all this stuff, and also from the point of view of new business models and contracting. So one of the mechanisms we have just mentioned here is the energy community, and regarding that, we do have our first speaker, Julio Diaz, who is a member of the Instituto de Tecnología Eléctrica, no? Energía. And he will just talk about the highest grid, which is one of the projects regarding the energy communities in Spain. And Julio, the floor is yours. I will share the presentation with the rest. Okay. Let me share the screen with you. Can you see this the presentation?
Yes, we can.
Okay, perfect. So Julio, it's yours.
Okay, good morning, everyone. We talk about the local energy communities with the characteristics of positive net balance. Okay. In the 2019, in the Clean Energy Package, the European Commission defined two kinds of energy communities: the citizen energy communities and the renewable energy communities. As you can see, it's no a global definition for energy community. In ITE, we are based on the definition of the Tineke, Banshore, and colleagues that can define the energy communities that are social movement that enables more participatory and democratic energy process. Okay, this is a concept that we can or we have a new energy model to lead the green energy transition. This green energy transition is focused on the citizen. The citizen is related to different renewable generations, and with different technologies to manage and monitor the generation. And in addition, we have another industrial sectors coupling to the community. Okay, in the Spanish government strategy, the idea of this green transition based on energy communities guide us to 2050 to electrical sector based in 100% renewable energy. Okay. Talking about energy communities, the energy communities is composed for several issues that I can show in this slide, since generation, distribution, energy supply, battery energy storage. But in addition, we have an energy market relationship, electrical vehicles, and energy efficiency services that are interconnected and related. Uh, for no in an only uh, relation itself, but it's a mixed and hybrid connection. Today we talk about the high-speed project. The high-speed project is a project granted for Spanish government. It's an excellent network of technological centers, Spanish technological centers. The concept is the Cervera Excellent Network is based on different topics where the different technological centers are specialized. In this case, we talk about hybrid energy systems. The hybrid project is based in local energy communities, but the particularity of positive net balance. This implies not only the possibility to the self-consumption, but the possibility to provide to the DSO energy supply or assistance to any fault or problem in the grid. Okay. We can show different key features of the hybrid project. The hybrid project is we studied different topics. Is forecast of generation and demand, the market system, the regulatory framework. But we are today we are focused on the design and planning of the energy community. The design and planning is based in the individual consumption, available resources, electricity tariff, and other parameters, and two types of models. First of all, we need to precising the service using an optimal methodology to determine the better installation for each community. In this optimal pre-dimensioning, we determine the peak power to be required, the better energy allocation criteria, and depending of the model that we use, the best investment ratio, the implementation surplus, etc. In the case of the definition of the electricity tariff that we use in an energy community, it's important to define the distribution or partition coefficient that can be static or dynamic. It's an agreement that all the members of the energy community that define previously to start the operation of the energy community. Okay, I comment to you that we have two models. The first model is energy as a service, and the other one is the energy as you invest. Energy as a service consists, at gross mode, in define a mathematical model when we use the aggregate demand and the energy capacity that can be provided for the energy community, plus the available budget and different possible scenarios, but defined on a energy cost function cost. Okay. This cost function we optimize using two criteria. To maximize social profile and maximize individual savings. And we have two main restrictions. Prioritize the self-consumption of the members of the energy community and the reduction of the energy poverty of the global community. Okay? The solution, we obtain the peak power that we need to require to install our energy community, and the individual fees and the partition coefficients that we provide to the different members of the community. Another model, the energy as you index, consists of different mathematical models in which consider only the individual demand profiles, the available budget, and the energy capacity of the community. In this case, the cost function optimize one optimized criteria that is to maximize individual profile in the fair way, and two restrictions, setting the investment percentage and setting the generation percentage. The solution, we have the peak power that we need to be installed, the investment ratios, and the partition coefficient. As can you see, the great difference of the two models are in the energy as your service. You have a global profile that you can provide to the different members based on the previous agreement. In the energy as you invest, your profile depends on your economic contribution or your generation contribution. In ITE, we studied these two types of model using our digital twin facilities. We have a pilot demonstrator called Gamma. In this in Gamma, we have two kinds of digital twins: an energy digital twin based on the monitoring of management of the different parameters of the energy community, and the electrical digital twin that is consists of an hardware in the loop and power hardware in the loop tools to certify and validate of the equipment that we use, and the testing of the different development that we can provide to the community. This is possible that in IT we have a real environment that consists on photovoltaic streams, a wind generator. We have two charging stations for electrical vehicles. We have energy battery systems, and we have a control center. Uh, we have in this slide the different features of our installation. And this is possible. We combine the physical environment one with the simulation environment. Thank you for your attention. And we have in IT, we are open or share any question that you have.
Thank you so much. Thank you so much, Julio. I will just share with you also in the meanwhile we are talking about the next speaker, the the QR sorry, here, the QR address of the project. So we have talked about the energy communities, but can we? The next question is: can we go beyond that limit of the energy communities? Can we think about something in different way of integration in that sense? So the answer is on Johannes Slasik. Johannes is a member of the Energy Institute of Johannes Kepler University in Linz. So I will just leave the floor for you, Johannes. You can share the screen if you want. You are muted, by the way.
Okay, one thing at a time. Welcome. And let me share my screen. Okay, and I hope you can see my screen now. And may I go ahead with my presentation? Would that work, Enrico?
Yeah, go ahead, Johannes. Yeah.
Okay, perfect. In this case, I think I'm presenting the eCrew project here. And I think it fits very well into this particular workshop where we talk about service integration. On the one hand, we establish energy communities, and eCrew is in particular establishing community renewable energy webs. So we are trying to establish virtual energy communities in a sense as a new business model, as a new aim. And thereby the already decentralized energy communities, we are trying to integrate them back into the system. And this in particular, I think, fits this workshop. And on the one hand, or on the other hand, also creates a new opportunity, a new business model, so to speak. So what did we do here in this study? We basically created a virtual platform, a virtual app that we can use, that energy communities can use, where consumers and prosumers are virtually connected, which means you apply, you sign up, you sign a contract, in this case, in particular, with the energy utility who is managing this app. So there is a very big partner actually for energy communities that we foresee, namely, well, the local, so to speak, energy retailer or energy utility management. They can service this virtual platform. They can gauge the energy flow. They can secure also the energy demand response in this sense, and also the demand management. Which means if we do not have enough, let's say, solar energy within our energy community, then of course we can feed in from the energy utility. On the other hand, if there may be in a great summer day, if there may be excess energy, for example, uh, prosumers within an energy community can sell that energy back to the energy utility. So this allows for also shifting like the peak loads. This is a big problematic situation within this energy transition that we have due to such a high energy demand, that we have such peaks, energy peaks in a sense. And then one question is how to eliminate or reduce these energy peaks. And with by creating this business model with our virtual energy communities, we actually established also a possibility, a room for shifting these energy peaks, so to speak. And how do we do that? Because of our digitalized platform or the app that the actual consumers and also the prosumers are going to use. Here, the energy utility can send up some nudging or push-up messages, so to speak. So they literally inform the consumers or also the prosumers that we have a very sunny day, that we have excess energy, that they should do the laundry now, or that they should turn on the dishwasher perhaps if possible now, or load their car, for example, now. But on the other hand, also push-up messages where they should reduce their energy consumption because tariff prices are currently very high, because there is not enough renewable energy, for example, available within the crew, within the energy community, and this is gauged by the energy utility. So here we create, in a very sense, a win-win-win situation. Namely, on the one hand, consumers are winning by gaining renewable energy from their neighbors, for example, from other prosumers. So they have green energy. Prosumers are winning because they are actually signing a contract. I mean, they're all signing a contract in this particular case. But prosumers are also signing a contract and are getting an incentive from because they share or literally they sell their excess energy. So any energy amount that the prosumers, they don't need themselves, they can sell to the community at a fairly reasonable price, much cheaper than the market tariffs currently are. And that's the second win situation, so to speak, for the prosumers. And the third win situation is actually for the energy utility. The energy utility suffers currently quite a bit because, on the one hand, we have high energy prices. Consumers are irritated and they don't know which energy utility perhaps to choose. They're also sometimes turning away from energy utilities, obviously, because of these decentralized happenings. So they are joining rather energy communities than staying with an energy utility. Well, there is a current trend, at least recognizable. So what can energy utilities do? By using this eCrew model as a business model, they can at least stay in contact with their consumers and also with prosumers. So they're not losing any customers. They at least can reduce their margins. They do have costs, obviously, and these costs continue to stay, whether consumers stay with the energy utilities or not. So they can at least stay in contact with the consumers and the prosumers, with their customers. They can reduce their margins, their costs, and also they have the opportunity to gain some excess energy from the prosumers. Well, at least probably in the summer month, which means that they can, and they also stay connected with the consumers in the sense that they can, because of these push-up messages, they can shift these peak loads. So they can ease out a bit of this energy pressure, of the demand pressure actually, by connecting with in this case, with virtual energy communities. to go on, originally we had created a sort of like a prototype, an app that was meant to show can we change the energy behavior, the consumption behavior of consumers. And with this app and this study, we recognized that because of push-up messages and because of nudging and also gamification, and basically gamification incentives, we can very quickly and very easily influence customers' decisions, and in this case, reduce the energy demand at certain points. Or if we have, for example, a very sunny day and we have a lot of PV power available, to increase the use of the energy use or the energy consumption at a certain time. For example, midday on a very sunny day, and we load our car, or we heat the pool if necessary, or we do the laundry, and so on. So here we proved that we truly can influence customers' decisions and create a behavioral change in energy consumption. And as a consequence, out of this prototype app, we developed this eCrew project, and we are in the middle of this eCrew development, so to speak. So we created now a platform where consumers and prosumers can log in and have a contract with the energy utility literally managing this platform. So they provide this service of creating this virtual energy community. And on this platform, we consumers and prosumers can literally see the real-time energy flows. Of course, consumers and prosumers need smart meters to do that. Therefore, the energy flow must be readable, so to speak. So we do need this consumption data to even be able to work with. This is in Germany already much broader installed. This smart meter system in Austria also very good installment. In other areas of Europe, this is a bit less or weaker in this case, but we are also working on that process simultaneously. So here on this dashboard, you see the energy flow from a prosumer to the consumer. You can see the kilowatts, so to speak, so the power that is needed, that is consumed, on the one hand by the whole community, and on the other hand by each individual household. But we can also see the feed in from the grid. How much is actually distributed, how much energy is distributed from the energy utility or the energy retailer at that. And this gives a good overview how much energy does this community need, and how much is provided by prosumers, let's say photovoltaic panels, and how much is provided by the grid. And to make this system now, this business model in a sense work, we need this split incentive system, which means that the consumers pay for getting either the energy from the prosumers, so let's say from their neighbors who have a photovoltaic panel, or from the grid. If they get it from the energy utility, from the grid, then they pay, in a sense, regular tariffs, regular market price, current market prices. Or there is excess energy in the community from the prosumers, then they can purchase at a much cheaper rate the excess energy from the prosumers. And on the other hand, the prosumers obviously can sell that energy. If there is excess energy available within the whole community, so also the consumers do not need to consume more energy than may be available, then this is in a sense a feed in back into the grid. So then the energy utility can sell at a much cheaper price than tariff prices green energy. This makes the energy utility in a sense greener to a certain degree, and also allows the energy utility to purchase at much cheaper tariffs or based on contracts, obviously, to purchase energy from the consumers, from the prosumers. So here, because of this split incentive system, we create finally this win-win-win situation. And if you have any questions to that, then we perhaps can talk about it later on. But this is in a sense our business model that we are trying to create. And for that, we set up now 3 lighthouse communities, one in Turkey, one in Spain, and one in Germany, to try to establish how is this going to work. In Spain, we do have members already, so all eCrew models in the lighthouse communities have been rolled out just recently, within the last few weeks. And in Spain, we have by now like 12 members. In Turkey, we have by far the most members, more than 1,800. However, about 250 members of those do not have smart meters. So they signed a contract, but we cannot actually work with them or with those households, unfortunately, because we cannot read their consumption data. And then we have a German lighthouse community in Bavaria, where we have currently 102 members, and 50 of which already are using the app and actually really engage. They get the push-up messages from their energy utility already. They react on it. They take in from the community the prosumer distributed energy, so to speak, so the green energy at a much cheaper rate. And we have first data available on that, how this system is going to work, or how the system is working. And as part of this setup, and with the experiences of the lighthouse communities, we are now rolling out like a CEO handbook, which means that other energy utilities or energy retailers literally have a guideline, a handbook on how to set up this eCrew model, this business model, how to roll out a virtual energy community, what are the enablers, what are the barriers, so they can better overcome some of the barriers and use the enablers in this sense. So I hope you understand or can gather this business model. And in the sense, it's also very important, this becomes a third business model for energy communities. We already have the renewable energy communities with a legal definition, as well as the citizens energy communities. And this is in a sense by having a platform managed by the energy utility. It's a third business model, a third opportunity for creating energy communities, however, managed by the energy utility. So the license also of sharing energy is with the energy utility. But it has been with the energy utility anyway. So you can actually bypass building any associations or cooperatives for creating energy communities, and leave that in a sense to the experts, to the energy utility management, who already have these experiences, who already know much more about the energy flows and the energy transfer, also the market and the tariffs and so on. So this, in a sense, we feel is actually a very good part of an integration. The energy community is a decentralized action, so to speak. And here with this business model, we integrate an energy community back into the system. However, again, yes, with a win-win-win situation here. And currently, we are working on our follower communities. So we have 3 lighthouse communities, and we approached 24 follower communities. And we have our next kickoff meeting on November 30th at the Enlit conference in Frankfurt. And here we are very eager, obviously, to gather and have as much follower communities built up as possible, mainly so we can have much more experience. Also perhaps in different countries, so we can see how our system works with different situations, different local situations, different sun. We have a different sun availability in Spain or in Turkey than we have in Germany, and so on. So I think this will be further down the road very exciting. Again, we are in the past the middle of the project. This project itself is running till June 23, so next year. And by then we have a CEO handbook for all energy utilities and retailers. However, because we're looking for follower communities, so please don't hesitate. Maybe you wanna get in contact with us. Right. Okay, what else? For any of the prosumers, we also have like a PV amortization calculator. So what does it take to invest in a PV panel, and how soon, within our crews, within our virtual energy communities, how soon can a PV panel pay off based on the split incentive system, based on the contract, so to speak. That said, finally, we have, in a sense, 3 crews established, one in Spain, one in Turkey, one in Germany. And there is a 4th that already applied with us. This is ACEA, is an Italian energy community that are also interested and willing to build a whole apartment block, use that as a crew, installing PV panels on the rooftop. So I think this will be also a very interesting, another, in a sense, lighthouse community. Okay, with that, I like to close my presentation. Thank you very much for your attention, and I look forward. If you have any questions, let me know.
Thank you so much, Johannes. I will just share with you all the the direction of the project. Cool. So you have talked also about the integration of the energy communities and all this stuff, and you have touched a special point also regarding the behavioral change. Really interesting. And all these systems just gather into grids, and more. They're getting more. They're getting smarter. So in this topic, we do have Giorgio Bonvicini, who is a member of the team in China, in project European projects. So he will introduce us the Muse Grids project. So Giorgio, I will just share with you the presentation. Okay, the whole screen and go.
Maybe for the people online, it's better that I sit. Thank you. Okay. So good morning, everybody. I'm Giorgio Bonvicini from RINA. RINA is the largest Italian engineering consulting company. We are very active in the European research projects, and specifically I am talking about the Muse Grids project, which is the acronym of Multi-Utility Smart Energy Grids. This is a project that we are coordinating as RINA. It started in 2018 and will going to finish next month in October this year. And it is a lighthouse project for Europe towards local energy independence via the promotion of smart energy systems. We have the partners that you can see here in this slide, in this map. You can see we have some clusters of members, of partners in Italy, in Belgium, Netherlands, and in Spain. Specifically, we have 2 demonstrators, 2 physical demo sites that are one in Osimo in Italy, Marche region, and one in Udeverly in Belgium, close to Brussels. And here we test some technologies for energy transition and integration of different energy systems. We also have virtual demo sites in different contexts. One is in Eilat in Israel, two of them are in Spain, Belen and San Ciprián de Campos, and one is in India, Kolkata. Then, both in the virtual demo sites and in the replication cities, replication sites that are in Riga, Porto, Constanta, Pesaro, and Cologne, these 5 cities with different features, one from the other. We are testing the use of an IT tool that we have developed together with the University of Aalborg. It is an improvement of the energy plan tool developed by Aalborg University in order to plan the transition of cities and districts towards renewable energy supply. We will see more in detail later the details. I was saying this project is about mainly smart energy systems. We are targeting different energy systems and different renewable energy sources. This slide is, in my opinion, the most important of the presentation, since it represents the different energy systems that we are studying and making tests and demonstrations about, and the different renewable energy sources. As you can see, we are working on electricity networks, on the hydrogen system, on natural gas networks, district heating network, cooling networks, water networks, and we are to do that. We are exploiting solar energy, wind, geothermal, waste heat, biomass, and mini hydro. Of course, traditionally, these sectors, these systems, these energy systems were considered as separate, one from the other, but several technologies exist that are highlighted here in this slide that can couple these sectors. And you can see highlighted those where we are working in Muse Grids. We want to create in Muse Grids a smart energy system which we define, as you can read here, as an approach in which smart electricity, thermal, water, gas grids are combined with storage technologies and coordinated to identify synergies in order to achieve an optimal solution for each individual sector and for the overall energy system. So to minimize primary energy demand, to minimize greenhouse gas, so CO2 emissions, and to minimize energy supply costs. Some of the technologies that we are testing in Muse Grids then that help in coupling the sectors that I have presented in the previous slide are, for example, power to heat and electric vehicles. We are using different types of power to heat devices to carry out smart heating of buildings, to exploit the excess from renewable energy production, mainly from solar, to produce heat, store it, and provide to the final user when needed. We have also a neighborhood battery for electricity storage in the demo in Udeverli, and a large thermal energy storage system in the Osimo demo site. I will show you later which are the results of the implementation of these technologies in the 2 demo sites. In addition, we have electric vehicles that not only allow reducing fossil fuel consumption, but also are exploited for vehicle-to-grid and vehicle-to-building applications. So we are using our vehicles as additional energy storage, electricity storages for the local grid and for the buildings. In addition to these 2 clusters of innovative technologies, we are managing a lot of existing assets in the 2 demo site that include cogeneration and renewable power plants, district heating network in Osimo, water network again in Osimo. Another important point of the project, as I have mentioned earlier, is the development of a planning tool for cities, the Muse Grids tool that is an upgrade of the energy plan tool developed by Aalborg University. This tool puts together algorithms for the mapping of the local energy demand, for the mapping of potential local energy supply in terms of sources, geographical distribution, and time distribution. It allows defining and creating some scenarios to simulate, and then can be applied to MuseGrid cities. We will apply it to the virtual, we are applying it to the virtual demo sites and to our replication cities, but you can download it from the MuseGrid's website and use for your case study. For example, here on the right, you can see the scenarios that we are modeling for Osimo, one of our demo sites. We are modeling, for example, the reference scenario, the baseline, with no changes in the energy systems. Then we are modeling an increase of individual heat pumps presence in the system. We are modeling some scenarios with an increase of the penetration of district heating in the local energy systems, again, an increase of renewable energy sources, an increase of, again, of the heat pumps plus renewable energy sources at a different extent, and then we also have some scenarios with electric vehicles and a combination of electric vehicles, heat pumps, and additional renewable power. Of course, it was too much to put in one single slide. Let's go to the results of the project. Here, I'm briefly summarizing some of the results related to Osimo demo site. Here, the main technologies that we have are a large thermal energy storage coupled with a cogeneration plant, and the main result is that the hourly operation hours of the cogeneration plant could be increased by 900 hours per year, so more or less by 10%, thanks to the presence of this storage, because, as you can see in the chart on the right, we managed to produce heat and consequently also electricity in the periods when the heating demand was lower, thanks to the presence of the storage system that could be filled in with the produced hot water. Then, thanks to the application of an algorithm for modeling a district heating network developed by Cartif, we managed to reduce the district heating supply temperature by 5 to 15 degrees for 50% of the year, and this also allowed a strong reduction of the primary energy demand and of the CO2 emission for district heating in Osimo. Then we have a significant electricity production from renewable sources. We have as assets managed by the demo responsible partners, 80 kilowatt of photovoltaic plants and 110 kilowatt of hydropower. Plus, there are in the area 33 megawatt of private renewable assets, mainly solar, but also biomass and biogas plants. In Osimo, we are also implementing some smart techniques for the monitoring and management of the water network that allowed saving 41,000 cubic meters per year of water losses, also implying electricity savings for pumping water and for water treatment. And then we are testing electric vehicles, vehicle to grid, and some smart heat pumps at the demo responsible headquarters. Of course, these are only tests with minor impact, but they are interesting. They have interesting results. As a result of the implementation of all these technological solutions, we have reduced CO2 emission by 128,000 tons per year. These are only preliminary results. In these days, I need to receive from the demo site the final monitoring data in order to calculate all of these KPIs that will be published in October, both for Osimo, for Udeverli, and for all the other activities also related to the MuseGrid tool, to business model, to regulatory aspect, etc. We will publish at the end of the project a project handbook that I invite you to download from the website of the project, and will collect all the experience developed within these 4 years of project. Now let's move to the second demo site, and let's approach the end of the presentation. The main project results for the demo in Belgium, Udeverli, are related to the integration of electricity storage systems in the local energy grid I need to anticipate that this is a really small village. It is mainly one road with 20, 30 houses, I don't remember. And they had initially problems with electricity supply since they have only one connection point and they suffered of blackouts or lack of power. So this is not only to reduce CO2 emission and improve the environmental aspects, but also to increase the security of supply for this district. The buildings in this district have photovoltaic plants. We have added some battery electricity storage system, thus increasing the electricity self-consumption of the photovoltaic plants by 38%. In addition, we have some electric vehicles and vehicle-to-grid chargers that allow benefits on the local grid since they constitute an additional battery-based storage system that increases the self-consumption of electricity from renewable sources and provides benefit to the local grid. We can see on the right, it is a bit small, I think, yes, sorry for this. The trend on the, level of charge of the battery in one of the electric vehicles in the bottom, and on the top the trend of electricity withdrawn and provided to the electricity grid. So here you can see that sometimes we are also providing electricity to the grid instead of only recharging the vehicles. In addition, with the same aim of increasing the self-consumption rate and coupling the electricity and thermal system and heating system, we have some smart heating systems that produce heat, hot water for heating, space heating, for domestic hot water production when there is a surplus of electricity production from renewables. The results, of course, this is a much smaller demonstrator compared to OSIM, with a reduction of CO2 emission by 131 tons per year of CO2. These are, again, preliminary results. Final results will be available in October. To conclude, we have seen in this project that there are many ways to achieve service integration and integration among different energy systems. And all of these solutions can lead to an increased flexibility of these energy networks, energy systems, and to an increased security of supply that today is a trending topic also for the geopolitical situation. We are promoting in Muse Grid service integration through an increased penetration of local renewable energy sources with energy storage systems, both electric and thermal, to the smart management of some loads, and to power-to-X solution. All of this is providing benefits in terms of increased self-production, security of supply, as I have mentioned, reduction of greenhouse gas and pollutant emission, and decrease of energy supply cost, which is also an important topic today. Just thank you for your attention. I would like to remind you, if you will be in Brussels, to visit us at the European Sustainable Energy Week, Energy Fair on September 28 and 29. We will have a booth as Muse Grid's project, and then we will have again in Brussels our final event on October 27. Thank you very much for your attention.
Thank you. I don't know if I'm pronouncing properly. Okay, thank you so much. I will show again to you the address of the project while we are just presenting the next speaker. And we have talked about really cool technical points, and another point is just the integration of the not only the technical part, technical aspects like utilities, but also the services, efficiency services, and their structure of contracting. So just applied to some specific commercial facilities. So this is as Smart Spin talks about. So we have Luciano. Luciano will just introduce us the Smart Spin project. So I will just
thank you, Enrico.
Yeah, I will leave you the floor. So you have the control, Luciano. Go ahead.
Okay, so I can share now. Okay. So in this presentation, first, I'm going to talk about the objectives, the concept, and the work plan of Smart Spin. Then there are some definitions of smart energy services. I'll talk about the split incentive issue. Then review some business models for energy service companies that can be used to deliver smart energy services to the commercial rented sector. Then I'll show the interviews that, the interviewees that we interviewed in Work Package 2. This work I'm going to show in this presentation is out of Work Package 2. Then talk about the energy efficiency as a service model and the energy savings model, and some recommendations that we have obtained out of the Work Package 2 research. We'll also show some published at least a list of published deliverables which are available on our website. Okay, so the Smart Spin objectives are, first of all, demonstrating the feasibility, the effectiveness, and the advantages of a business model that can deliver both energy and non-energy benefits through smart services offered to the commercial rented sector in Europe, of course. We are going to address the barriers that prevent the commercial rented sector from engaging with the energy service companies and implementing energy efficiency measures, and also the performance-based contracting. We also have tasks related to big data utilization to actually design better control systems of energy consumption in buildings, and to measure accurately the energy savings. This is part of Work Package 4. Then we have another goal, that is to design new contractual templates. So this business model will not only be abstract model, but will be usable through the templates that will be designed to deploy the smart energy services. And last point, an objective is to engage and train key market stakeholders, and it can be ESCOs, landlords, tenants, industry bodies, energy experts, and so on. And the goal is to allow them to deploy the smart spin business model in the commercial rented sector. So what is the main concept of the smart spin? Here, the main concept is that basically we have a split incentive situation here, where the building owner is not incentivized in investing in energy efficiency to improve the energy efficiency of their building, because they would not enjoy immediately the benefits. The tenant in it is living in is occupying the building, and is paying the energy bill, or they are paying to an energy provider for the energy consumed. But what is proposed in Smart Spin is that they would also pay for the energy saved to an efficiency provider, which can be an ESCO, and the ESCO would install and maintain energy efficiency measures in the building, and share the value of these savings with the building owner. So with this mechanism, the building owner would be incentivized in giving a permission and engaging with the ESCO, and giving the ESCO permission to start to have this energy efficiency project delivered. The work plan is the one you see in this figure. So now we are at the end of year one. So the project started the 1st of September 2021. so the work package 2, we have done a review of smart energy services market for the commercial rented sector. And actually what I'm going to show you in this presentation is the outcome of work package 2. So then in the following work packages, these recommendations will be used to design the contractual service, and then the data analytics that I mentioned with managing the big data from the demo sites, and the energy management algorithm, then the demonstration and the validation at the demo sites. We have 3 demo sites in Ireland, in Greece, and in Spain. And then work package 6 will be about the business model definition. So in work package 6, that actually starts now. So in year 2 is starting. We will use the previous recommendations and the service definition to formalize the business model. And then we have, of course, communication, dissemination, engagement, and exploitation activities. Energy services, as you know, there are several definitions in the literature. The one I like the most is maybe the last one. Energy services are provided through a combination of capital equipment, labor, materials, and energy, and they are an essential feature. An essential feature of an energy service is the useful work that can be measured in a variety of ways, definition given by Sorrell. In our case, we also consider energy services that are a combination of capital equipment, labor, materials, and energy. But the issue that we face in the sector is the split incentive. And the split incentive occurs where the benefits of a transaction, which in this case is the installation of energy efficiency measures, do not primarily accrue to the person who pays for it. So if the landlord is paying for the energy efficiency measures, he will not enjoy the benefits because the energy bill is paid by the tenant. And also the energy efficiency directive is in Article 19, is recognizing the importance of addressing the barrier of split incentives in the building sector. So this is a well-known problem at European, at the level of the European Commission, and the issue is that there are no rules, so absence of rules for dividing the costs and the benefits between the parties. And the model that I showed, or the concept that I showed in the first slide, is actually the basic idea that we are using to overcome the split incentive. So to have the tenant that is paying for the energy savings, he is paying a fee to the ESCO, and the ESCO sharing the value with the landlord. But of course, that's very high level model, and we did a review in work package 2, and several variants and models, possible business models have been identified, and the final model, of course, will be given later in the project in work package 6. But for now, I would say we had a deliverable where we reviewed the business models. Then there are some business models have been proposed in the literature, and these are the shared savings business model, the guaranteed savings, the SHAFI, and also the energy efficiency as a service. But at least the first 3 were given without considering the split incentive scenario that we are considering in Smart Spin. So these models originally have deal only with an ESCO and with its client, whereas we are considering a split incentive. So the first one, in the first model, the landlord and the energy service company would share the energy savings, and this is similar to the first scheme that I showed you. And the tenant is going to pay the energy supplier for the energy consumed and get energy from the energy supplier, but is also paying the ESCO for the service. And actually, the ESCO, typically in this model, is also responsible for financing and financing the project and implementing it. So the ESCO would have and performance contracting agreement with the landlord. Next model is guaranteed savings. So in this case, the ESCO is not responsible for financing the project, but there is an agreement with the landlord to deliver a certain minimum level of savings. So there is performance guarantee. And this seems the most promising and applicable model to what we are going to do in SmartSpin. We are also having a meeting with our external advisory board to have discussions about the possible models and the market at European level. So this seems one of the maybe the most applicable model because typically the landlord had a fund for funding the energy efficiency measures, and the ESCO, most of ESCOs would deliver their services using a performance guarantee. There is also another option where the ESCO would be responsible for the operation and maintenance of the entire energy system, and could transform the energy system also to achieve energy efficiency targets. And the ESCO would take all the savings if the targets are met. Otherwise, they would pay a compensation to the landlord corresponding to the energy shortage. And the landlord would have a contract with the ESCO for energy and energy efficiency. And the landlord would also bill the tenant for the energy expenses, and these are mainly the energy consumption of the tenant. And this is also a type of model that could be applicable because sometimes the landlord is billing the tenant, so the tenant does not have directly a contract with an energy supplier, but the landlord is billing the tenant for the consumption and is getting paid by the tenant. Last model, actually there are more, but in this presentation I also show the most important ones. The energy efficiency as a service business model. Here we would have two companies actually delivering energy efficiency to the tenant and to the landlord. The energy service company would be responsible for equipment installation and maintenance in the building owned by the landlord, and they would deliver energy savings to an efficiency provider who is providing the capital for the project. And the energy efficiency provider is actually the company that is delivering the service and that receives a performance-based payment. So also in this case, the payment is subject to the achievement of some energy performances, energy savings, or energy cost reductions. In work package 2, we had 10 interviews with key stakeholders. You see the list in this page. We have landlords, we have energy consultants, we have ESCOs, we have associations of ESCOs. We also have an interviewee from the European Commission who wanted to be anonymous. So with these interviews, we gathered a lot of relevant information to validate our findings and the literature review we did in work package 2. Another key feature of the SmartSpin model is that the model applies considering two different periods or steps, which can be called the guarantee periods if using the language of energy performance contracting. In the first step or period, the ESCO would engage with the tenant, and in this case, what is recommended is installing energy efficiency measures that concern the energy management. So there is also an advice on how to reduce energy consumption and to install or replace energy efficient equipment which is owned by the tenant. And of course, in this period, there will be some target energy savings, and there will be penalty for the ESCO if not achieving the target savings. And there will be a service level agreement that is considering the user satisfaction, typically the thermal comfort. And this part will be covered in work package 3. So it's work that is currently being developed. And in the second period, the contract will also include the building owner. And in this case, more powerful energy efficiency measures can be installed and agreed with the ESCO. And so what it is expected is that in the second period, there will be higher energy savings, but higher costs as well for the energy efficiency measures. And after the guarantee period number 2, as you know, the contract with the ESCO ends, and the building owner or occupier is earning all the savings out of the project. And yeah, this diagram shows what happens with the SmartSpin energy savings model. So we have first that initial energy costs are rather high, but then during the first step, these costs are reduced through installation of certain through energy efficiency measures and improved energy management. And of course, there are some costs that, in light blue, which are low, because typically these measures are not very costly, are not as efficient as the measures in the second period. In second period, you see that the yellow part is lower, so there is a reduction, further reduction in the energy consumption, but there are very likely higher costs for implementing these measures. But at some point, the contract expires, and you see that the energy consumption remains low compared to the initial situation, but all the savings can be earned by the building's occupier. And this is actually what we see in SmartSpin compared to the classical EPC that you see in the corner on the right-hand side and the top right-hand side. We have actually only one client for the ESCO, so it's an agreement between the client and ESCO. What are the recommendations that we have actually provided to the colleagues working in work package 3 of SmartSpin? So the energy as a service, or energy efficiency as a service, covers energy management, maintenance, a total guarantee of equipment, improvement works, and improvement of energy efficiency. And this is similar to energy performance contracting. And the SmartSpin service, what we see in terms of service, is a service that covers energy management, also opportunities in switching the electricity supplier, maybe with one that is cheaper, and then installation of energy efficient equipment or renewables like solar PV, installation or replacement, and also the operation and maintenance services. Another recommendation is to establish a measurement and verification process which is standardized, that ensures no measurement errors and is trusted by stakeholders, because this might be a barrier in deploying energy efficiency as a service in the commercial rented sector. So lack of trust in the MMV process. We also find that green leases are maybe the basic tool to allow engagement of landlord and tenants for improving sustainability and energy efficiency in the rented commercial buildings. It means that when the landlord and tenants sign a contract for renting the building, they will add some clauses related to sustainability and energy efficiency that will allow to later on to have a plan to improve energy efficiency and to get the energy and non-energy benefits previously mentioned. And there are two cases that are relevant with the service. In the first case, the landlord is owning the space and the equipment, but in some other cases, the landlord may only own the space. So if the equipment is owned by the tenant, then the model that it has been shown in this presentation is really the one that is needed because the energy efficiency measure can be first applied to the equipment owned by the tenant, and after that engaging also with the landlord. And so what is emerging out of this analysis is that the energy performance contracting could become a tripartite agreement between three parties, whereas traditionally the state of the art is that we have one client and the ESCO. It also we also found that sub-metering is also important, and our demo sites are being retrofitted with the sub meters because we want actually to bill the tenants for the actual energy consumption and not as usually it is done with based on the surface or the size of the rented unit, to have a fair energy tariff. And this is also the last point. So there are some stakeholders that are concerned about fairness of the energy tariff. This tariff sometimes is made dependent on the season, but it's something that is unwanted. So they want a tariff independent on the season, which is fair and then easy to understand by tenants. On our website, smartspin.eu/results, there are some public deliverables available, and actually we are going to add 2.4 is not that there yet, and 2.4 would be about the recommendations for the service, and it's basically what we have showed in this presentation. And yeah, I think this is the end. Thank you very much.
Thank you so much, Luciano. That's been a really interesting application of the energy as service and efficiency point of view, like a service integration and a framework of contracting schemes, like structures, typical EPCs, and the natural evolution of these contractings towards the facilities in this sense. I will let you also elaborate. So the natural partner of this kind of concept, this kind of structures, is obviously the pay for performance P4P pricing. So the master and commander in this topic is our next speaker, Sotiris Papadelis, who is the CEO of HEFS Intelligence. So I will let you the floor, Sotiris.
Hello, let me share my screen. Select window entire. Allow. You can see my screen, yes?
Not yet, in my case, not yet. Maybe Sotiris, if you choose the whole screen. Yes, right now. Yeah. Okay.
You can see it. Okay, so I'm Sotiris Papadelis. I'm part of the Sensei project. And let me share a few details about the project. So, the acronym of Sensei stands for Smart Energy Services to improve the energy efficiency of the European building stock. This is the website of the project, Sensei Horizon 2020 EU. The duration is 3 years, but we got 6-month extension, so it will end on Friday 2023, and this is the list of the partners. The goal of the Sensei project is to propose services that allow energy efficiency to be treated as a transactable asset, and this means to be able to buy and sell energy efficiency and compensate energy efficiency, as well as business models that utilize the services in order to valorize energy efficiency as a grid resource. The whole idea behind Sensei was that when you think in terms of the challenges of the power grid and the demand side capabilities and options that you have to address them, usually it's demand response, flexible demand. But energy efficiency also has a role to play. And the concept of Sensei was formed by looking at examples in the US, mainly California, also Vermont, and now there are examples also in Canada, where energy efficiency is treated and valorized as a grid resource. So this value that energy efficiency can have for the energy grid is recognized, quantified, and compensated. And in these cases, in these examples in the US, the scheme, the vehicle for compensating energy efficiency is the pay for performance concept. The main premise of this concept is simple. You compensate an asset or a service, in our case, energy efficiency, and the impacts of energy efficiency, according to what actually was the impact of the intervention. Not dim savings, not theoretical ex-ante estimations, but actual impact. And we know that performance-based agreements already exist, and they are part of the ESCO model when you're talking about energy performance contracting. Sensei focuses on designing public programs that support energy efficiency and also incorporate this performance-based concept. So they compensate, pay energy efficiency retrofits based on the energy savings they actually deliver. A series of arguments. There's 3 arguments, really, the main arguments of Sensei. The first is that pay for performance increases the impact of public programs for energy efficiency financing by introducing accountability. And this should be obvious. If you compensate based on what has actually happened instead of an ex-ante estimation, you probably get more results for the same amount of money. Now, the idea is that pay for performance should not completely replace grants and subsidies, because we know that subsidizing the upfront investment cost is a strong driver for energy efficiency upgrades, and in particular for deep retrofits. The idea is to use pay for performance for a part of these grants and subsidies, and linking part of the subsidies to exports results in impact helps increase the cost effectiveness of public programs. And one can think of it as imposing an upper bound to the acceptable amount of euros per megawatt hour saved. This is a bit similar to the idea of energy efficiency auctions, but pay for performance has a different approach and some unique advantages that I will talk about in a moment. Now, okay, it's obvious that P4P improves accountability and use of public financing. Okay, we have the benefits, but do the benefits outweigh its implementation costs? Because if you want to introduce pay for performance, you need new approaches, new governance structures, new tools, new infrastructure. And the question is, what's the balance between benefits and costs? Sensei as a project cannot answer because we need pilots, P4P pilots for that. But we approach it in a way that says, maybe we can find synergies so that to increase benefits for the same costs. So now that we have this tool that's pay for performance, what else can we get from introducing it to energy efficiency financing? And this leads us to the second argument that says pay for performance can and should be used to offer a premium to energy efficiency projects when their implementation is beneficial for the power grid, when their implementation leads to load shape changes that are beneficial for the grid's operation and aligned to its challenges. The asterisk in should is because all the other alternatives that a system operator has at their disposal to address the challenge of the power grid, capacity reserves, demand response, are compensated based on performance. So if you want to treat energy efficiency on equal basis with these alternative options, you have to adopt a pay-for-performance approach. Now, Sensei has demonstrated, and by that I mean there is a deliverable that has a methodology, uses real data, and leads to some specific conclusions that A, energy efficiency is valuable when its impact is aligned with persistent needs of the power grid. And what we really mean when we say that is that energy efficiency can displace capacity reserves, can help phase out lands that are all polluting and exist mainly to offer capacity reserves. And that the design of a program that compensates energy efficiency for this contribution does not need a radically new toolset, but can be done using tools that power system operators already use, tools and methodologies that already are used when system operators perform capacity adequacy studies. And to demonstrate that this is actually a case, we have developed and open sourced a tool that quantifies energy efficiency value. And the whole approach that this tool uses is the capacity adequacy analysis. The only difference is that, contrary to the standard approach of the capacity adequacy studies, where demand is treated as something exogenous and fixed, this tool allows the introduction of load shaping resources that can strategically reduce load in specific hours of the year. And this helps in what? This helps because if then you have a project and a before and after energy efficiency project, and a before and after profile of the demand, you can quantify its impact because you can quantify the extent to which it helped reduce the need for reserves. Third argument. Pay-for-performance programs can incentivize the development of the know-how and infrastructure that are necessary for energy retrofit project aggregation. Usually when the discussion is about energy efficiency upscaling and how to attract private financing and blend it with public financing, the answer is always aggregation. We need a lot of projects bundled together. And aggregation is useful, but the question is, who's going to do it? Who in the market right now has incentive to create the structures and the technical capabilities to support aggregation of energy efficiency projects? If there were incentives already, strong enough at least, we would have seen cases of aggregation. And the argument of Sensei is that P4P programs create a market for aggregation because they create a need. and a value for aggregation. And this goes along with the development of governance structures and technical capabilities that are necessary to support it. And by governance structures, I mean mainly this idea of sensei of a pay-for-performance program facilitator. This is a third party that is responsible for running a P4P program on behalf of the corresponding program owner. And there are two deliverables in sensei for that. And two, because this concept of program facilitator is approached in two different ways. The first deliverable finds similarities between a P4P program facilitator and EPC, and an EPC, energy performance contracting facilitator. We know that EPC facilitators have helped create markets for EPCs in European countries, for instance, Belgium. And the idea was, what can we learn from this market making, market creation approach? And the second deliverable is more technical. So it approaches the program facilitator as a technology provider, as a platform provider. And you can find similarities with demand response program facilitators, such as what Honeywell is and does in the US. You actually provide the platform, the technology platform that links demand side, HVAC systems mainly, with the power system signals and requirements for flexibility. And in terms of technical capabilities, we have identified two main aspects. The first is the capability to screen and evaluate potential projects to include in a pay-for-performance scheme, based mainly on data, because if you're talking about aggregation and portfolios, you cannot visit its individual building. You have to use just data. And the second capability is the measurement and verification of the impact from the retrofit. And for this, there is a deliverable that outlines a specific methodology and a specific tool that's also open sourced. The idea behind that tool, and has its name inside, is that to add some additional capabilities to the standard approach of measurement and verification, which is predicting. Okay. Typically, measurement and verification is just a prediction approach. You use some observable variables, and then you have consumption. You create a model during the baseline period, and you use this model during the after retrofit, the reporting period, to create a counterfactual of the energy consumption that would have been if the intervention had not taken place. And that part is just a prediction part. And for that, there is already a lot of tools and a lot of literature, because a prediction problem can be addressed in many different ways. What Insight adds is some additional capabilities that are more about understanding what's happening inside the building, using just data from it, and also helping matching the before and after conditions. So it has capabilities of inferring occupancy and occupancy levels to help this matching before and after, to summarize consumption into a small number of energy consumption profiles that can also help this mapping, to find strange days, discords, so to exclude from this mapping. All of this mainly to help test a hypothesis that says that before and after, the only thing that actually changed is the intervention. All the differences that I actually see between before and after are due to the intervention inside the building. Now, conclusions. The energy efficiency services sector is lagging behind renewable energy generation in terms of demand for investments and business models for aggregating projects. There are a lot of business models for energy generation. If you say, let's install solar panels on a building, then you have business models for the deployment, for the financing, for sharing the benefits, and etc. The moment you say, let's take these business models and try to apply them in the energy efficiency case, it becomes more difficult. Because it's more difficult to measure. Energy efficiency is a lot of different interventions, not just one. Installing solar panels, more risks, either real or perceived. And while there is a lot of work that has taken place in measuring the savings and covering risks and uncertainties at the individual project level, scaling this process up to portfolio level still faces challenges. So the main argument, to summarize the arguments mentioned before, of Sensei is that designing and rolling out P4P pilots can lay the groundwork for the development of new methods and standards that are necessary for creating large-scale pipelines of projects. So while performance gives some specific benefits, accountability, the way public financing works, and the ability to compensate energy efficiency for its contribution to the grid, which can also be seen in an alternative way, the ability to use incentives to steer energy efficiency interventions towards measures that are more beneficial for the grid than others. You get the extra benefit of methods and standards that helping aggregation of projects. And there is a need, definitely a need for P4P pilots in the European Union, because they are an effective use of public finance to discover best practices for aggregation. And also they can act as a workbench for developing financing tools and risk allocation mechanisms that are important, especially if one aspires to attract private financing and blend public and private financing to support energy efficiency. And that has been all. Thank you very much.
So the last project is just a mixture of all these services, contractings, and all this stuff. So it is called Neon, and it is going to be presented for myself. My name is Eneco. I'm part of R2M Energy. I'm R2M Solution Spain R&D group, investigation group. So let me just share with you the screen. Just a moment, please. Okay, can you see the screen, Luciano? Okay, I think so. So I will try to be really brief because we are running out of time. But basically, Neon is a project integrated into the Horizon 2020 framework, and it talks about the energy community, in energy communities themselves, and the integration of services into these energy communities, and also the contracting of these communities. So This is the bunch of the partners in this project, in this CSE. So what we do, what we pursue in this NEON project. First of all, we have to take into account that we based on the environmental basis and also the social basis. Like we talk about the reduction of the poverty, energy poverty, and all this stuff. And taking into account those two pillars of the project, we pursue the integration of the cross services integration, talking about the PP, renewable energy, the contractings, and all this stuff. Also, new innovative business models, just integrating those contractings like performance contracting on B4P, as Otis has explained. Also, the digitalization of these energy communities. This is must, obviously. Also, the flexibility, not in terms of energy sharing, but in terms of the life behavior of this community. How can we change, or how can we modify these communities? Also, we include the facilities, not only the residential ones, also the commercial and urban economy facilities, and finally, obviously, the validation of these scenarios. So, how do we start? We just touched three basic points. One is the identification of the services, because each of the energy communities is different. The result of which service can we integrate. Also, the engagement of the people. I assume that many of the attendees we are engineers, so we have something like urticaria or just this kind of scratchy skins, thinking quantifying formulas. So, but in this case, this is important, the psychological part. How do we integrate? How do we set the guidelines for the integration and engagement of the people? And finally, how do we integrate all this into the energy community? The next question, the next natural question is the legality and how do we pay these energy communities? So we have to remember again the society part, and the environmental part. And here we first look to the legal and financial conditions for these services, because maybe it is different, the integration of those services, of those legal and financial conditions of the services regarding the energy communities. An example is just the energy community itself, or an industrial workshop, for example, when we integrate the PV. Another point is the financing mechanisms we do have, not only public ones, also the private ones, and the available tools which are related. So yeah, the mortgages, the collective mortgages, and all this stuff before the contracting phase. Also, there can be some gaps between the different situations, financial situations, the needs of the energy communities. Also, the enabling factors. We are talking mainly about the municipalities, for example, the town halls and local authorities, for example, and finally the feasibility of economic feasibility of these structures and the integration of the services. We also have to talk about the maths, because it's really important, because of the previous presentations. Here we integrate also all the parts coming from the grid, demand response, flexibility, application, etc. We integrate also terminal units. We are talking about terminal units in terms of treatment, air treatment, also the production and generation, all its range. And also, it is in fashion, but it's really useful. Also, all the aspects regarding the predictive data analytics in optimization, mathematical optimization, and all this is just go through the platform, corresponding platform. It's a really standard, and really easy to implement in this case. So finally, we also have the quantification of all this stuff. So first we are talking about the impact in terms of economy, the impact in terms of the social benefits, the environmental benefits, all this stuff, all together with the ethical structure. So we here implement the DLT layer technology. So this is within the methodology established for the quantification of this impact, energy impact, economical impact. Those are the basis of the technology of the quantification of these energy communities. And we also have the integration of the pay for performance schemes, which together with the EPC and as Luciano has explained, and so this has started to explain, they are the perfect, we guess at least that they are the perfect mechanisms for the integration of the contracting, the smart contracting within the energy communities. And finally, the smart contracts also together with blockchain and all the security issue solver systems. So this is the basic one. And now, how do we validate it? We do have 4 sites, 2 in France, Domaine de Sox and Stone City, another one in Spain, Polígono de las Cabezas, which is just in the south, and in Italy, Berchita. Those are our different scenarios. Some of them are fully residential, some of them are industrial mixed with the residential ones with electrical vehicle, and there is one specifically, the Stone City, which is fully office and industrial environment. So we do have a really very good bunch of situations to test these technologies. So this is a really big presentation from the NEON project. Thank you so much. Thank you so much to all of you for attending, the speakers. We really appreciate it. And just thank you so much for your contributions, and hope to see you again really soon, other events. Thank you so much.